All right, so we're going to start off this week by looking at 3.5. And as I mentioned earlier, it's basically a review of section 3.4. We're going to be finding roots again. The general strategies we're going to try to always do is to take anything that's not a quadratic and turn it into a quadratic by using synthetic division. Because every time you divide through synthetically by a root, you take your polynomial and you bring the degree down 1. Right? So if we can get it down to a quadratic, then we can solve it. In order to figure out what number we have to divide by, we don't want to just try to guess what could be a root. We'll use the rational root theorem. Right? So all the problems that we do that have polynomials that are higher degree are going to have a root that's a fraction. If it didn't, you wouldn't be able to do it. At least not with the methods I've shown you. Right, so just a couple reminders that, remember, if you have a number that is a 0, it's also called a root, and it's also called an x-intercept. Just summarizing that again. A 0 is a number that you can plug in to a function and get an answer of 0. Of course, if you plug in a number and the result comes out to 0, that's the y value coming out to 0. If you ever have a coordinate with the y value is 0, that is called an x-intercept. Okay. So let's take a look at this. So if a polynomial does not cross the x-axis, it doesn't mean that there aren't any roots. It just means that they're not necessarily real. Remember what we've said before is every polynomial has as many answers as its highest exponent, always, okay, when you're finding roots. Sometimes the answers are real, sometimes they're imaginary, and sometimes they're repeated. Sometimes they're not distinct answers. You may have the same answer repeated twice. Let's take a look at this. Okay, y equals x squared plus 1. If I graph that, that is a parabola that has been shifted up 1. And if we look at that, does that ever cross the x-axis? No. So in this case, it means there are no real solutions. Now, if we take a look at this and start to solve it, set it equal to 0. If we subtract 1 from each side, we get that. And Madison, what would be my next step to get x by itself?
You would square each side.
So if we square each side, we would have that.
You would take the square root of
Okay. Yeah. So we'll take the square root of each side. And when you do that, those cancel out. But now we have something kind of weird here. We have the answer as plus or minus the square root of negative 1. Well, whenever we take the square root of a negative, we've talked about that not being in the domain of a polynomial, but not in the domain of real numbers. It's going to be imaginary. So what we'll quickly do is go through a little bit of a review on imaginary numbers. And then after we finish that review, we'll get to the material in the section. So first thing that I have in red there, that box, something you learned in Algebra 2, okay, and that is a definition. Right? I equals the square root of negative 1. That is not something you can prove. It'd be kind of like if somebody said, prove that parallel lines never cross. You can't. You can't prove that. It's one of those things that everybody just says, okay, we'll just go with it, and we can build other things off of that. Right? So same thing here. This is a definition. Can't prove it. But we can prove other things based off of it. Like this, I squared. So I squared would really mean to take I, which is that, and square it. So I squared means take the square root of -1 and square it. And what would you get if you did that? Yeah.
-1.
Yeah, you would get -1. So that's kind of an interesting result, that when we take an imaginary number like I and square it, it actually turns into a real number. So that happens. And the point there is that anytime you end up with I squared in a problem, you should always change it to -1. Okay, we don't want to leave I squared in a final answer. Now, let's take I, plug it into the previous equation, and see what happens. I'm going to plug in I for x. And what did we just say I squared was? -1. So now you have -1 plus 1, and -1 plus 1 equals 0. So what does that mean about I in this equation? I is a what? Yeah. I is a root. It's one of the roots of that equation. So is -I. We're going to learn that whenever you have a complex root in a polynomial, they always occur in pairs. They have to. You can't have an odd amount of complex roots. If you have one, then you have two. And the second one is very easy to find if you know the first one. Very easy. And we'll talk about that. So, complex numbers, in general, are written in the form a plus bi. A is what we call the real part. B is what we call the imaginary part. So technically, every number that you study is a complex number. It's just that sometimes B is 0. So sometimes numbers are just real. They don't have the imaginary part. It's still complex, just the imaginary part is 0, so we don't write it. These are all examples of complex numbers. 3i, -7i. These first two are called pure imaginary numbers because they don't have a real part. This third one, 4, it's a complex number, but we can be a little more specific. Usually we just call that a real number. And this is a complex number that has both a real and an imaginary part. The real part is 2, the imaginary part is 3. 2 plus 3i. And then down here is another complex number that has both a real part and an imaginary part. Real part is 2/5, imaginary part, -1. So notice when I'm describing the real and imaginary part, the real part is the number without the I, and the imaginary part is the number in front of the I. That's the imaginary part. Okay. Any questions on that? Okay. So, in order to say that two complex numbers are the same, you have to check two things. Two complex numbers to be the same, the real parts have to match, and the imaginary parts have to match. Here's an example of two complex numbers that are the same. 2 plus 3i, 2 plus 3i. Now, if I did something like this, those aren't the same. You might think, well, part of them's the same, so does that make them the same? No. They both have to have the same real part, and they both have to have the same imaginary part to be the same. Any questions on that idea? It's a pretty simple idea, but still important to mention. All right. So now we're going to do a really quick review of how we add, subtract, multiply, and divide complex numbers. So remember that I, if I go back to it, is the square root of -1. I is not a variable when we do complex numbers. I is a symbol that stands for square root negative 1. Okay? Just like when you use, let's see, think of like pi, right? When you write 3 pi. That's a letter in the Greek alphabet, but am I using it as a variable here? Variable means it has no fixed value. So am I using that as a variable? No. Pi stands for 3.14. If you were going to do a problem and you had to pick a letter to represent your variable, you should never pick this letter. It's a very bad letter to pick because in math, that letter is something special. It means 3.14. Same thing with I. In math, especially when you're dealing with complex numbers, you should never pick I as a variable in a word problem because I means something special. Okay, it's not a variable. But if you treat it like a variable when you're combining like terms, that will help you think of how to do it. Like when you do 2x plus 3x, you get 5x. Well, if you do 2i plus 3i, you do get 5i. Right? So think of it as a letter, think of it as a variable when you're combining like terms. But don't ever actually use it as like a variable in a word problem. Pick a different letter besides I. When we do multiplication of complex numbers, especially when they have real and imaginary parts, we're going to have to FOIL. And foiling is going to lead to having lots of I squareds. So remember, we have to change those. If we have to divide complex numbers, what we actually do is we end up multiplying. We end up multiplying by something special called the conjugate. So I'll explain what that is. And now for square roots, let's look at this. Sophie, what number, when I have square root negative x, what number is really in front of the negative x even though we haven't written it?
Or in front of negative?
In front of the, the coefficient of the x.
Well, I don't know.
Yeah?
1.
Technically there's a 1 here. It's really a negative 1. Like there's a negative 1 in front of the x. Right? If you have this, then it would be like having a 1. But that means you have a negative 1. So it's really negative 1 times x. So everyone agree you could write it that way? Right? And then whenever you have a product under a square root, you can separate that into 2 roots. Like that. Square root of negative 1 times the square root of x. And Leanne, which one of these can I simplify? Because we have a definition for it. That's a hint.
Negative 1.
The square root of negative 1 is what? I. So what we've basically done is we've separated it so we didn't have a negative under the square root anymore, at least the second one. And the first one simplifies to something nice. It's I times the square root of x. So the trick here is anytime you have a negative number under the square root, you can pull the negative out as an I and then just leave the other thing under the root. Now, when I wrote down earlier how to write complex numbers, I put the I after. But when I wrote it with this square root, I put the I before. Anybody know why I put the I before the square root? It has to do with eliminating some confusion. Anyone know what I'm trying to avoid? Yeah?
Is it to avoid making it look like a variable?
Well, we already know I is never going to be a variable. So we can assume that all week. So we don't have to worry about whether or not I is a variable or not. I'll tell you right now, it's not all week. Yeah?
Square root and square root.
I don't want it to look like the I could be under the square root, because it's not. Right? If you write something like this, it's very hard for me to tell whether or not you really mean for I to be under the square root or not. So when you have a square root, if you put the I in front, it eliminates that confusion completely. When you don't have a square root, you can put the I at the end. Something like this. That's how we normally do it. Right, so it's just with square roots, we put it in front. All right, so let's look at this one. Using what I explained up above, anyone think they can tell me the square root of -4? And there's no plus or minus in front. So I'm just asking for the square root of -4. Yep.
I square root 4.
So yep, you could start off with I square root of 4. And this is a case where the square root of 4 does simplify to, yeah,
2i.
2i. If that square root of 4 was a square root of 5, we would have left it exactly the way you wrote it. Okay, but 2i, final answer. All right, how about this one? Square root of -7. Mabel?
I square root of 7.
Yep, that's one where you can't simplify the square root, so we're going to leave it, and we put the I in front. All right, how about square root of -9? Yes,
3i.
3i, good. And how about the square root of -20? Sophie?
It's like 2i square root of 5.
Perfect. 2i square root of 5. So it's just like you would simplify square root of 20, 2 square roots of 5. But the negative is going to come out as an I, so that's why we put it in front. Any questions on that? All right. Let's look at addition. So we'll do one of each. One add, subtract, multiply, and divide. Normally when I teach it from scratch, I go through lots of examples, but hopefully you guys will kind of recall from Algebra 2 a little bit. Okay, so when you're adding complex numbers, think of it as combining like terms. You can combine real parts, and you can combine imaginary parts. And that's it. All right. Anyone think they could tell me what you get when you add those two complex numbers together? Caleb?
Would be 11 plus 2i.
So we got 7 plus 4, that's the real part. And we know we're doing addition because that's the symbol between them. That gives me 11. Then we've got a -3i plus 5i, -3 plus 5, 11 plus 2i. Perfect. Now with subtraction, you want to kind of think of that as a distributive property. Think of it like this. You're subtracting the 6 and you're subtracting the I from what's in the first parentheses. Anyone think they can tell me what you get here? Tim?
-2 minus 3i.
So we've got 4 minus 6, -2, and then -2i minus I. -2 minus 3i. Any questions on adding or subtracting? Let's go to multiplying. So multiplying, remember what I said earlier, it's like FOIL, right? Or double distributive property. So I'll kind of go through the first one with you, and then we're going to end up doing another multiplication problem because that's how you have to do division. You have to know how to multiply. So Madison, what is 2 times 5? 10. And Sophie, 2 times -i?
-2i.
2i. Maddie, 3i times 5?
15i.
15i. And now the last part, we'll be a little bit careful with it. First of all, it's a positive times a negative. Start with that. Lindsay, what's a positive times a negative?
A negative.
negative. And Nick, what's 3i times I? I already took care of the negative.
3i squared.
3i squared. So it's a negative 3i squared. When you're done, your final answer should always look like this. Real part, plus or minus, and then an imaginary part. So that's not a final answer. All right, so we got 10. And again, if I combine my i's, what do I get?
13i.
13i. And now we've got minus 3 times I squared. Minus 3 times, and Mabel, what did we say I squared was?
Negative 1.
-1. So that's a minus a minus. That's going to be minus minus 3. So that's going to turn into a plus. Final answer, 13 plus 13i. Just a coincidence, they both came out to 13. All right. Any question on multiplying? Okay, and dividing. So in order to divide, we have to know what a conjugate is. So a conjugate of a complex number is when you change the sign or negate the imaginary part. Negate means make it the opposite. So if you had a complex number a plus bi, the conjugate is a minus bi. And remember earlier when I said to you, if you're solving for roots and you have one complex answer, you always have two? Well, complex roots always occur in conjugate pairs. Always. So if you're solving a problem and you find that it has a complex root 3 plus 2i, well, guess what? 3 minus 2i is also an answer. Okay, so complex roots always occur in conjugate pairs. Always. Alright, so let's just practice looking at a number and then identifying the conjugate. So Tim, what's the conjugate of 3 plus 2i?
3 minus 2i.
Yep. And Julie, what's the conjugate of 4 minus 5i?
4 plus 5i.
4 plus 5i. All right. How about 3i? Caleb, what's the conjugate of 3i?
Negative 3i.
Good. And Madison, what's the conjugate of 6?
Negative 6.
What's the imaginary part here? If I wanted to actually write it, it'd be like 6 plus what?
I. Or 6.
Let's say you wanted to write it like this. What would go in the first box?
6.
And in the second box?
0.
0. So this number is really 6 plus 0i. So that would mean the conjugate would be
6 minus 0i.
6 minus 0i, which is really just what?
6 minus I. Or 6 minus 0.
Which is
6.
6. So when you have a real number, the conjugate is the same. 6 plus 0i is the same as 6 minus 0i. Questions on finding conjugates? Okay, so now, whenever we have to divide complex numbers, you're not allowed to leave I in the bottom. Can't do it. This is how you fix that. To get the I out of the bottom, you multiply the numerator and the denominator by the conjugate of what's in the bottom. So to do division, we really turn it into multiplication. So let's try dividing that. And then we're really gonna start the section. Which, it's all stuff you already know how to do. Rational root theorem and synthetic division. But now we know how to work with complex numbers, so we'll add in some examples that have complex answers. All right. So we've got 5 plus I divided by 2 minus 3i. First thing I like to do, I put everything in parentheses, because I know I'm going to have lots of distributive property going on. And Julie, what am I going to multiply top and bottom by here?
2 plus 3i.
2 plus 3i. I can already tell you the bottom is going to come out to 13. And there's a way I did that in my head very fast. And the reason I can do it fast is because the bottom is multiplying 2 minus 3i times 2 plus 3i. Those are conjugates. Anytime you FOIL conjugates, there's a trick. And I'll show you what that trick is right now. The top I can't do quite as fast. So, you FOIL out what's in the bottom. What's 2 times 2? 4. 2 times 3i? 6i. And 2 times negative 3i? Negative 6i. So what happens there? Cancel. So when you're doing, if you learned it as FOIL, you don't have to worry about the O and the I, the outer and the inner. They're going to cancel every time you do conjugates. So that's part of the trick. And now, this part, what's negative 3i times positive 3i?
Negative 9i squared.
Negative 9i squared. So we already know this is gone. And I end up with 4. I squared is what number? And what's negative 1 times negative 9? 9. Remember how I told you it was 13? So all you have to do is take this number and square it. Take this number and square it. And you might say, well, does it matter? Wait, what if you square the negative with it? It doesn't matter, the negative is going to go away. Take the real part, square it, take the number right in front of I, square it, and add them up. All right, so just kind of like a quick, another little example. You don't write this down. If I had to do this problem, the answer would be 25 plus 9, or 34. Square the 5, square the 3, add them up, and there you go. If you don't want to use that trick, you don't have to. You can FOIL it out every time. You're just going to be doing more work that's going to cancel out. Yeah?
Is there any exceptions?
Nope. Nope. That always works. All right. So we've got 4 plus 9, or 13. Now, the top, I'm going to have to go through and do all that out. So we get 10. And let's try to do some of it as we go. 15i plus 2i. What's 15i plus 2i? 17i. I times 3i. What's that going to be when we simplify it as much as you can?
3.
Nope. Positive I times positive 3i. Negative 3. Right. Positive I times positive 3i is 3i squared. That's 3 times negative 1, or negative 3. So when I'm doing complex arithmetic, especially at this level, I usually kind of just jump to that simplified part. Now we only have really 2 steps left. 10 minus 3 gives me 7, plus 17i over 13. Now, that's not standard form. Okay? It's supposed to look like this. Real part, plus or minus, imaginary part. So the way we finish this off to make it look like it's in this format is you just divide each number separately by 13. Just separate it out. So the real part is 7/13, and the imaginary part is 17/13. So I might set up a question like that on Edulastic where I put two separate boxes and I say identify the real and imaginary part. The real part is not 7, it's 7/13. And it's just plus, I'm sorry. Not plus or minus. It could be minus, but in this case it is a plus because that's how the numbers worked out. Okay, any questions on that? All right, so that's all the background with complex numbers. And it's exactly when I wanted to finish in the first half. And now the second part today, we're going to go through and use synthetic division, rational root theorem, quadratic formula, and find roots. So, is this a problem where I need to use synthetic division to solve? Why not? Because what? We can easily factor it. I don't know if you're going to be able to factor it using real numbers. What did you try to factor it as?
I haven't tried it just
Oh.
yet.
Okay. Yeah, if you try to factor it, that's not going to factor with real numbers. So because it doesn't factor, do we need to use synthetic division? So we're going to set that equal to 0. How do we solve it? Why? Why don't I just use synthetic division? Why can we use quadratic formula? If you're going to have problems today, you're not going to be able to use quadratic formula. Like that one. Why can't I use quadratic formula on that one? It's not a quadratic. So the whole goal is to get something to be a quadratic. If it already is, well then life is going to be pretty simple. You don't have to use synthetic division, rational root theorem. You just plug into quadratic formula, you're done. Right? So in this case, A, B, and C are all what? They're all 1. So we got negative B plus or minus the square root of B squared 4 times A times C all over 2A. And what ends up, how about, Maddie, what ends up under the square root?
-3.
Yep, good, -3 over 2. And I need to simplify the square root of -3, which we talked about earlier. Lindsay, how do I simplify square root of -3?
I square root 3.
There you go. 1 plus or minus I square root 3 over 2. There are your answers. And notice there's a pair of them. They're imaginary and they're conjugates. -1 plus I root 3 over 2, -1 minus I root 3 over 2. Now, you might say, well, you didn't write that in standard form. You're right, I didn't. I could. And if you want it in standard form, which the directions did ask for, you would write it like this. There's your standard form. The real part is -1/2, and the imaginary part is root 3 over 2, and I put an I next to it so you know it's imaginary. Okay. Any questions how what I have here and over here are the same? Especially in a multiple choice question. You may see it one of these two ways. You just have to know they're the same. All right, so this is getting at what I keep saying to you. So notice that the roots we just had in the last problem were conjugates. One was the real part plus the imaginary, and the other one was the real part minus the same imaginary. So if you have a complex root, let's say you know 2 plus 5i is a root. It is guaranteed 2 minus 5a. 2 minus 5i is also a root. Complex roots always occur in conjugates. And notice at the end here, I write this as long as b isn't equal to 0. Well, that's because if you knew 3 was a root, essentially you know 3 plus 0i is a root. Well, then that means 3 minus 0i is a root. That doesn't tell you anything else. That's because 3 is a real number. Right? This theorem is useful when you have imaginary roots. So the remainder theorem, factor theorem, synthetic division, everything that we learned last week still works with complex numbers. It's just a little bit more complicated of a number to work with than what we've had before. So, let's show that 1 minus 2i is a root of that. Now, I don't want to plug in 1 minus 2i. I could plug in for x and see if I get 0 for y. That's going to be a lot of work, because I've got to raise this thing to the 4th power, then multiply it by 4, and then square it, multiply it by 17, and then add it to what I had before. That's a lot of work. So what's another way to show something is a root that we learned last week? Yeah?
It makes the equation 0.
So when you plug it in, it would make the equation 0. But that's going to be a lot of work to plug it in for x. We're going to have a lot of FOILing, especially to that 4th power. That's going to be pretty bad. Yep?
Does that count as like x minus 3? So you can do the quick trick thing? I don't know what it's called. But like when you just have that next to it when you bring down the coefficients.
Yeah, what is that called? Anyone remember? Synthetic division, yes. Instead of proving 1 minus 2i is a root, let's prove that x minus it is a factor. Right? X minus this is a factor. To prove that this is a factor, divide through by it synthetically, and we're going to hope that we get what?
0.
0 for the remainder, yes. So again, it's going to be a little bit more annoying because we have to do this synthetic division with a complex number, but let's see what happens. So we've got 4, at least we're going to have a 0 at one step, that's nice. 17, 14, 65. So because this is going to involve some FOILing with complex numbers, I'm going to do some work off to the side to keep the synthetic division nice and organized. So the first part's not bad. Bring down the 4. What's 1 minus 2i times 4?
4 minus 8i.
4 minus 8i. Everything here is a distributive property. Okay? So multiply the 4 to both. And luckily we had a 0 in the next spot, so that makes it nice. When we add the columns, we get 4 minus 8i. Now off to the side, I need to FOIL this. 1 minus 2i times 4 minus 8i. So we're going to get 4 minus 8i minus another 8i. That's minus 16i. If I make a mistake, just let me know. And what's negative 2i times negative 8i? 16, yeah?
I squared.
I squared. And what is 16i squared? What number?
Negative 16.
Yes. So that's going to give me negative 12 minus 16i. And luckily, we only have 2 steps left, so we're not going to have to FOIL 20 times, okay? Now, add these up. Well, there's nothing to combine that with. What's 17 plus negative 12? 5. All right, now let's do it again. 1 minus 2i times 5 minus 16i. Let's see what we get. So we're going to get 5 minus 16i minus 10. What's minus 16 minus 10? Negative 26. Negative 2i times negative 16i is 32i squared, which is what number? Negative 32. 5 minus 32 is how much? Negative 27 minus 26i. And now we're at the last step, and hopefully we get a negative 65 right here, so we get a 0 remainder. That's the goal. Okay, so we got negative 26i. What's 14 plus negative 27? Negative 13. Okay, so last FOIL. Okay, just to be clear, these are my columns in case you're confused. All right, let's see. 1 minus 2i times negative 13 minus 26i. All right. 1 times negative 13. 1 times negative 26i is how much? Nick?
Negative 26i.
Negative 26i. And what's 2i times negative 13? Oh, Caleb?
26i.
26i. Looking good. You're supposed to get 65, so let's see what happens. Negative 2, the negative 65. Negative 2i times negative 26i. That's a 52i squared, which is really what number? Negative 52. And what's negative 13 minus 52? Negative 65. Perfect. So we just showed that 1 minus 2i is a root of f of x. Now, based on what I said earlier, what else has to be a root here that you know right now without any more work? Yep, Caleb.
1 plus 2i.
Yep, 1 plus 2i. So if 1 minus 2i is a root, you're guaranteed 1 plus 2i is a root as well. All right, so a little annoying with synthetic division, but you'd never have to do, most of the time I'd probably take one step out here, so you may have to do foiling one less time than this. Yep.
So like the quotient would be pretty complicated then, right?
Yeah, so when we look at the quotient here, it has imaginary coefficients. We wouldn't really be working with polynomials that had a quotient like this, so we won't really ever do anything with the quotient at this point. Yeah. All right. How come every odd degree polynomial will always have at least one real zero? Always. Yep.
Because they infinitely go in both directions. So
And-
one side raises upwards infinitely, and the other side decreases infinitely.
Yep, so that's a big part of it. One side goes up forever, one side goes down forever, and the graph is what kind of graph? Yep.
I was going to say that the odd numbers don't have the conjugate. Like there's one that won't have like a pair.
This one won't have a pair? Or it will?
Well, like
Oh, you're saying, okay. So when you have odd, like a cubic polynomial, there's different kind of scenarios that could happen. As far as your answers, you could get 3 real and no imaginary. That's definitely possible. Could you get 2 real and 1 imaginary? Why not? Why couldn't we have 2 and 1?
there be a conjugate.
there would have to be a conjugate. Remember, imaginary roots always come in pairs, so it's impossible to get 2 and 1. So these are the only scenarios that could happen in this problem. 3 real, no imaginaries. 1 real, 2 imaginary. How come no real? Why can't I have 0 and 3? Yep.
Well, the grammar was minus my cross x-axis into ones.
Yeah, because it's a continuous function and it goes up and down forever. It's going across the x-axis at least once. So we're always going to have at least 1 real root. And the fact here, if you look at the table, you couldn't have a 0 and a 3 because now you have an odd number of imaginary roots. That can't happen. They have to occur in pairs. Now, when I say 3 answers here, I'm not saying they're distinct. Maybe the same answer 3 times, right? If you FOILed out something like x minus 2, x minus 2, x minus 2, you would get a cubic polynomial, and the only answer to it would be 2. But it would be what we call a repeated root. Okay. So any questions on why odd degree polynomials will always cross the x-axis at least once? And that's going to be the whole goal to solving a problem like this. We have to be able to find at least 1 rational root and divide by it to turn this into a quadratic. So let's see if we can figure out a rational root. How do I figure out, what's my first step in trying to find a possible rational root to this problem? Tim?
Get into quadratic form.
Okay, and how, so now let's work our way back up. How are we going to get it into quadratic formula?
By factoring.
If you remember how to factor something like that, you could, but it is a cubic. So we do have to turn the cubic into a quadratic, but how? Yeah?
Rational root.
We need a number to divide through by synthetically. How do you get that number? Rational root theorem. All right. P, Q. How about, Maddie, what are my possible values for P here? 1, negative 1, that's it? And how about my values for Q? Same thing. So all the possible rational roots are what? Yeah.
1 and negative 1.
Yeah, there's not much going on here. Just 1 and negative 1. I can quickly, normally I would graph at this point to narrow this list down. There's only 2 in the list, and I can plug them in for x and check them faster than I can graph them. Which one of these numbers works if you plug it in for x and you get 0? What is it?
1.
Positive 1. Yep. So now we know, right? Find all roots or zeros. We have 1. And now let's see what the other 2 are. Put that on the outside of my synthetic division. And what are going to be my coefficients I write down?
1, 0, 0, 0.
Good. We don't want to forget those ones that are missing. All right, this is going to be super fast because it's all 1s and 0s. Break down the 1, multiply, add, multiply, add, multiply, add. There we go. Now, look at this. 1, 1, 1. Have we seen that today? A is 1, B is 1, C is 1?
Yeah.
We already did this problem. This is this problem now. Now, you would be finding the roots of 1x squared plus 1x plus 1. Well, we already know what they are. Negative 1/2 plus or minus root 3 over 2i. So, negative 1/2 plus or minus root 3 over 2i. So, in this case, it worked out to be that situation. 1 real, 2 imaginary. So we had to find a root first using the rational root theorem. We checked it, plugged it in, it worked. Divided through by it synthetically, and then got a problem that we already proved before. Any question on it?
How would you get the roots from that?
From this?
Yes.
That's the example we did earlier.
I know, but if you didn't have the example,
Well, you'd have to set A equal to 1, B equal to 1, C equal to 1, and then do quadratic
okay.
formula. Yep. And then once you do quadratic formula, you'll get that.
okay, thank you.
Yep. But that's the goal, trying to get it down to a quadratic every time. So look back at example 6 for a second. F of x equals x cubed minus 1. If you set that equal to 0, and you try to solve it, you basically have this. And you're taking the cube root of each side. That's what you just figured out. This problem where you found these roots, you basically solved this equation. You told me all the cube roots of the number 1. And there are 3. 1 is a cube root of 1. This is a cube root of 1 with the plus, and then another cube root of 1 is with a minus. So when we're finding roots, when you think of it like this, there's always as many roots as there are your exponent. Always. Sometimes they're real, sometimes they're imaginary. So what we did in that problem was we found all the cube roots of the number 1. Or in our book, sometimes they refer to that as unity, finding the cube roots of unity. So in general, if you're solving this equation, you are finding the nth roots of unity. Because think about if you were to try to solve this. Your first step would be to add 1 to both sides. And your next step would be to take the nth root of both sides. So take the nth root on the left, take the nth root on the right, and you get x equals the nth root of 1. Now, calculator can't give you the imaginary answers. Okay, we have to find those by hand. So to solve a problem like this, you always want to go about it just like we did the last problem. You guys didn't even really know we were finding the cube roots of 1 here. I mean, maybe if you thought about rewriting it to get x by itself, you would have thought of it that way. But I didn't do that. Okay? I jumped right to the rational root theorem, and that's always what you want to do. All right, let's try another one of those, except this time they're going to tell us up front, find the 4th roots of unity. So what we have to do here is rewrite that as an equation. X to the n minus 1 equals 0. That's our template. And what is n going to be in this case? 4. So we are solving this equation, which, if you thought about it from a perspective of getting x by itself, you would add 1 to both sides, and then you would take the 4th root on both sides. But that doesn't really help us. Yes, that's what we're doing, but the calculator, if you type in the 4th root of 1, the calculator is just going to tell you 1. It's not going to give you the other 3 answers. So, we could use rational root theorem. Downside is this is a 4. So if you use rational root theorem, you're going to find a root. You're going to have to divide through by it, and then you'll have a cubic. That's still no good. Then you're going to have to do rational root theorem again to get it down to a quadratic. That's factorable. We don't need rational root theorem. Okay. Anytime I can avoid rational root theorem in synthetic division, I try to, because that takes longer. Anybody see how we can factor what's on the left? Yep, so
X squared plus 1, x squared minus 1.
good. X squared plus 1, x squared minus 1. Now you've got two quadratics. You could use quadratic formula on each of them if you wanted. I still think that's more work. Because now I can just solve them. Regular algebra, don't need anything fancy. And x squared minus 1 actually factors again. How does x squared minus 1 factor? Yeah, Caleb?
X plus 1, x minus 1.
There you go. So remember, we're looking for 4 answers to this problem. What do we get from those two? X equals, how about the first one? -1. The second one? 1. So there's 2 answers. Now, let's solve this. Set it equal to 0. We've already solved this today. It's one of the first things I put up. What's the square root of -1? Pi. So remember, when you take a square root on both sides, you get positive or negative. So the fourth roots of the number 1 are 1, -1, I, -I. Those are all the answers. And there's many ways you could go about that. The long, very long way would be to use rational root theorem, synthetic division, quadratic formula, but it would all work. That's going to take you at least 3 or 4 times as long. All right, any question on that one? Okay. So, notice in all the problems, and I've said this a lot, but go back and look at examples 4 through 6. The number of answers that you got in the question was always equal to the degree of the polynomial. We had a degree 4, actually, we had degree 4. We got 4 answers. We had a degree 3. We got 3 answers. That will always happen. Always. And that leads us to basically 2 theorems that are very similar. Right. The first one is the fundamental theorem of algebra. Which basically, this one says if you have a polynomial with a degree greater than 0 and real coefficients, okay, not the kind of coefficients that when Tim looked at it, he said, wow, that'd be a pretty awful quotient to deal with because it had imaginary coefficients. Not that. As long as you have a polynomial with real coefficients, then when you solve it, you're guaranteed to get at least one complex 0. This is a very non-specific theorem. Basically, all it tells you is that if you try to solve a problem, you're guaranteed to find an answer. I mean, it doesn't really tell you a lot. So any polynomial that has a degree greater than 0 will always have at least one solution. Well, we can be even more specific than that with this theorem and say not only if you have a polynomial that's degree greater than 0 will you at least have one solution, but if you have a polynomial with degree greater than 0, then you will have exactly n solutions. So not even saying you're going to have at least one, I'm going to tell you exactly how many you're going to have, and that's what the linear factorization theorem is. Because remember, number of roots and number of factors always go together. Number of roots, number of factors, number of x-intercepts. All the same thing. So let's say you were to try to factor this one. You'd have to use the rational root theorem, hopefully find one, then use synthetic division, and then maybe from there you could factor it or use quadratic formula. Okay, but I've already factored it, and it does factor very nicely. It factors as x plus 1, x plus 2, x minus 3. The highest exponent is a 3. 3 factors. So if you see directions that ask you to fully factor something, you're probably looking for as many factors as there are in the exponent. So I would give you a problem that had an exponent of like 6, 7, and say fully factor it. That's going to take a while. But a 3, yeah, definitely. And at this point, you guys should know how to do this, because you can see the roots are -1, -2, +3. They're all nice roots. They're all rational. So rational root theorem will help you get all of those. Here's another example. This would be coming from a 5th degree polynomial, because there's 1, 2, 3, 4, 5 factors. But the roots aren't distinct. There are 5 answers. -1, -1, 2, 2, and 2. Those are your 5 answers. But what we would say here is -1 is repeated twice. That's called a root of multiplicity 2. And 2 occurs as an answer 3 times. Multiplicity 3 means it's repeated 3 times. All right. So any questions on that? So that's 3-5. So tonight in the homework you'll see problems just like 3-4, finding roots, except now you might get some imaginary answers. All right, so those are the questions on page 193. We will take a look at that first thing tomorrow. And tomorrow, remember, we're going to do 3-7 and 4-1. And then our last section of the week will be 4-2. And just a reminder again, grades close next Friday. So this is the last week of academics for term 1.